Hey everyone and welcome. Today we're diving deep into what is really a masterclass on a fundamental challenge in pretty much all of engineering and data science. How do we look at a bunch of data and find the single best mathematical model to explain it? Now this entire explainer is based on some fantastic material prepared by Dr. Mahdian, so a huge thank you to him for putting together such a clear and insightful guide. All right, let's get into it. So here's our game plan. We're going to start with the big question. What does best even mean when we're talking about models? From there, we'll lock in our guiding principle. Good models are good predictors. Then we'll dig into the absolute bedrock of all of this, the least squares method. See where it starts to break down in the real world, and then this is the cool part. We're going to pull it all together into one unified framework that really puts you, the practitioner, in the driver's seat.
All right, so let's start right at the beginning. We are faced with a challenge that is, and I'm not exaggerating, at the very heart of so much of modern science and engineering. Just take a look at this. Those orange dots, that's reality. That's the data we've actually measured from some system out in the world. And those gray lines? Well, those are all the different stories we could tell about that data, all the different candidate models. One's a straight line, another's a wiggly curve. The huge question is, how do we get past just, squinting at it and saying, that one looks good? How do we find an objective, mathematical, defensible way to pick one and say, this is the best one? That's the problem we have to solve.
To answer that, we really need a philosophy, a North Star to guide us. And it turns out the most powerful, and honestly the most intuitive principle, is all about looking ahead. And this slide makes that principle concrete. You see, a good model isn't just about fitting the data we already have. Its real job is to predict what's coming next. On this graph, the orange dots, y of t, are the real measurements. The blue line, which we call y of t, that's our model's best guess. And that little gap between them, that vertical yellow line labeled epsilon, that's the prediction error. Our entire mission, the whole point of this, is to find the model that makes that whole sequence of errors as tiny as possible.
Okay, so that leads to the next logical question, right? We've got an error for every single point in time, a whole long list of them. We can't just minimize all of them at once. We need a way to boil all of that information down into a single number, like a final grade for our model that tells us how well it did overall. So how on earth do we do that? And the answer is a mathematical tool called a norm. Now, don't let the name intimidate you. All it does is take our entire messy list of errors and crunches it down into one single meaningful number. And this is where you, the engineer, the data scientist, you start to get some control. As you can see here, you can choose different norms. An L1 norm, for instance, is great if you have a lot of weird outliers. But the most common one, the L2 norm, squares the errors, and squaring things means that big mistakes get penalized a lot, which is often exactly what we want. This choice of norm is really our first big decision.
And that choice, deciding to use that quadratic L2 norm, leads us directly to the single most important, most foundational method in all of statistical modeling.
The least squares method is just beautiful in its simplicity. Step 1, we start with a simple assumption that our system can be reasonably described by a linear model. Step 2, we define our prediction error, just like we saw before, the gap between reality and our guess. And then, step 3, this is the magic part. We find the specific model parameters that make the sum of the squares of all those errors as small as it can possibly be. We're not minimizing the errors, we're minimizing their squares. That's the whole idea.
Now, you can totally solve this with a bunch of calculus and algebra, and you'll get a formula. But just staring at a formula, it doesn't give you that gut feeling, that intuition. This quote here hints at something much deeper, a really beautiful geometric picture that makes it all just click into place.
And here it is. This is that beautiful geometric meaning. Forget the scary formula for a second. Just imagine that all of your measurements, that whole vector y, exists as a single point in space. And all the possible predictions your model can make, they're forced to live on that blue plane, that subspace. The least squares formula does something that is just brilliantly simple. It finds the point on that plane, y, that is geometrically closest to your actual data, y. The error we're minimizing is literally the shortest possible distance from our data to the world our model lives in. It's just an elegant projection.
So, when does this amazing method work perfectly? Well, it needs two ideal conditions. First, you have to have picked the right kind of model. And second, the noise affecting your data has to be white noise. Just think of it like pure, unpredictable TV static. It's totally random with no patterns and no memory. If you've got those two things, then the least squares estimate is as good as it gets. It's unbiased, meaning it gets the right answer on average, and it's consistent, which means it gets more and more accurate the more data you feed it.
But you knew there was a but coming, right? Of course, the real world is almost never that clean and ideal. And that's exactly when we start to see the limits of this simple, beautiful approach. Two big real-world problems tend to pop up. On the left, we have non-uniform noise. You can think of a sensor that gets less reliable the hotter it gets, so some data points are just fuzzier than others. But the real villain, the one that causes the most trouble, is on the right, colored noise. This is when the errors aren't random anymore. They have a memory. A positive error now makes another positive error more likely. This is a total disaster for simple least squares because the model gets confused. It can't tell the difference between the system's real behavior and the pattern in the noise, and that leads to a biased answer that won't get better no matter how much data you collect.
Now, for that first problem, the non-uniform noise, we have a really elegant fix. It's called weighted least squares. And the idea is just super intuitive. Instead of treating all the errors equally, we give them weights. We tell the algorithm, hey, pay more attention to the measurements we trust and kind of ignore the ones that are super noisy. And you can see it in action. The WLS fit line gets pulled toward the clean, reliable data, correctly brushing off the influence of those noisy outliers. Okay, so we've seen the basic method and we've seen how it can break. Now it's time to zoom out, to climb up to a higher vantage point and see how all of these pieces fit together into a single, incredibly powerful framework. A much, much deeper level of understanding comes when we switch our perspective. Instead of thinking about our data point by point in time, we can look at it in the frequency domain. Now, thanks to a beautiful piece of math called Parsible's theorem, we know that minimizing the sum of squared errors over time is exactly the same thing as minimizing the total error energy across all frequencies. They are literally two sides of the very same coin. And this lets us see everything we've been doing in a totally new light.
So what? Why does this matter? Well, here is the huge, game-changing insight this new perspective gives us. The model fit isn't uniform. The model is actually forced to become most accurate where your input signal has the most energy. This is a really big deal. It means your experiment design is not a passive activity. It's an active tool. If you want your model to be really accurate at high frequencies, you have to design an experiment that pumps a lot of energy into the system at those high frequencies.
And this brings us to the grand unified theory of it all. The big picture. Everything we have talked about, from the simplest least squares to more complex methods, they can all be seen as just different paths you can take within this one single framework called the prediction error method, or PEM. The power is entirely in your hands. You, the practitioner, get to choose the model structure. You get to choose the error norm, maybe L2 for least squares, maybe L1 for robustness, and you get to design the experiment. These three choices are the ingredients you feed into this minimization problem, and together they completely define your final result.
So, let's distill all of this down. Let's boil it down to the absolute guiding principles you need to walk away with to really achieve a level of mastery in system identification.
Here they are, your three key takeaways. Number 1, the core philosophy. It's all about one thing: minimizing prediction error. A model is only as good as its crystal ball. That's it. Number 2, the foundation. Least squares is your home base. It's simple, it's intuitive, and it's the conceptual launchpad for everything else. And number 3, the power of insight. That frequency domain view is your secret weapon. It proves that you are not just a passive observer. You are an active participant, shaping your model's final form through the choices you make.
And this final quote just says it all perfectly. Mastery isn't about memorizing 100 different algorithms. It's about getting this unified framework deep into your bones. Because that understanding is what allows you to stop blindly applying tools and start intelligently designing a solution that is tailored perfectly to the specific problem you're trying to solve. So there you have it. That's the journey from a simple, intuitive principle to a powerful, unified perspective on how we find models from data. The framework is now yours. So the only question left is, what problem are you going to go out and solve with it? Thanks for watching.